Thank you for the introduction. So yes, hi, I'm Matt, and today I'm going to be talking to you about writing allocation-free code in C#. This is a topic which has kind of got a fair bit of popularity in the last sort of year or two, really. There's a lot more of a focus on performance within .NET and writing code, and one of the aspects of that is writing allocation-free code. And I'm going to start with a very, very simple bit of advice, really. And if I go to my slides, simple bit of advice is don't worry about this. Don't bother about this. You're not going to need this. This is going to be a talk really about micro optimizations. And on the whole, your average application probably doesn't need to do this. Unless, of course, you actually do need to do this, when you do need to have a look at what's going on with your code and see whether or not you need to make it faster or whatnot. So really the key thing I want to say for this talk really is the message that I want you to take back is really to always be measuring. Don't just take my word for something here. Don't just do something because it looks cool on a presentation, but profile your application, see what it needs. And if it needs some help now, I can show you some interesting techniques for what we can do. But first and foremost, make sure you are profiling and that everything, you're doing these changes for the right reasons. Okay, so why am I talking about allocation-free code in C#? C# is a it's a managed language. We've been told continuously that the managed memory is cheap. It's nice and cheap. It's very easy to allocate memory in .NET, and .NET takes care of everything for us. And yes, managed memory is cheap, but it's probably more correct to say that allocations are cheap. So it's very, very easy to allocate memory in .NET. It's pretty much moving a pointer on a big block of memory until you've got more and more memory in use. So allocations are cheap, but the flip side to that is that garbage collection is expensive. When you do a garbage collection in .NET, generally speaking, the whole application is frozen. The runtime does a lot of work looking for all the objects that can be cleaned up. It'll clean those up. It'll compact all of your objects and your memory there, and then start everything back up again. So garbage collections are an expensive thing, and ideally we want to avoid those if possible. And so one of the key words I want to sort of focus on today is throughput here, and the idea of not necessarily performance and memory profiling to reduce the amount of memory you use. So like your application, what am I trying to say? It's try and reduce the amount of memory that your application is using in a single go, but over time. So it's about memory traffic. So you can have peak memory, which is low, say, using 500 megabytes, but then churning away and having memory traffic all the time, causing garbage collections. So throughput is the thing I mean here. So more allocations mean more garbage collections. If garbage collections introduce pauses will disrupt your throughput. So instead of having nice and smooth, reliable responsiveness, you actually get pauses introduced into the running of your application there. So the key thing here is better throughput means a smoother application, not necessarily a faster one. So you can write a bit of code here now. If I showed you some things now where you reduce the amount of allocations you have, if you reduce the amount of garbage collections you have, you can make your process smoother, but that's not necessarily going to make it faster, but it's going to be a better experience all around. So better throughput is actually good for when you need low latency. So things like servers, you want to always be able to get a fast response from a server. Same with games or interactive user interfaces. You need those to be responsive. So you want good throughput for those there. And if you look at that as well, servers, games, and interactive UI, that covers a lot of the things that we actually build. And so all of this stuff is applicable to nearly everything we're running, apart from, say, an overnight batch process. And this is a good example of what I'm talking about, really. We had a tweet a while back, and I forgot to get the name of the person who tweeted this. But talking about a feature which we've got in JetBrains Rider called dynamic program analysis. This is a feature which is sort of continuously monitoring your application when you run it, and it will report in the IDE common errors and common problems. And this feature actually showed that there was 13 gigabytes of memory allocated on application start. And this wasn't necessarily using 13 gigabytes all at once, but it was allocating, garbage collecting, and so on. And just changing that small bit of code there reduced all that allocation. And again, not necessarily speeding the application up, but makes the whole process smoother. So it can have quite a big impact. There are a couple of other reasons why we'd want to have a look at sort of allocation-free type code and reducing the amount of memory that you're using. One of which is if you're working in a constrained environment. So if you've got, if you're working on such as on mobile devices, such as cell phones or tablets, or games consoles, or also containers. If we're doing a lot more servers which are going to be based in virtual environments and running on the cloud and in containers and so on, we want to be able to reduce the amount of resources they use because we are paying by resource. So it can actually keep things cheaper if we use less resources. So using less memory is a good thing. And on a less powerful device, for example, garbage collection can be slower, so it can actually be more noticeable. The more memory we're using, the more we're affecting throughputs. It can be more obvious when we're using a less powerful device. And again, fewer garbage collections are useful for battery life as well. So if we're talking about mobiles and mobile devices, then we want to be able to reduce the amount of work we're doing because we can then have more battery life. And it all boils down to throughput. One of the more interesting things is that mobile gaming as an industry is a huge deal, and so you always want to try and improve your performance and keep things working, and again keep the battery life as high as you can. But one of the other reasons that I want to talk about is basically so that you know your platform. And the idea here is that even if you don't use it, you're still using it because it's still baked into the platform. Performance has become a key part of the design of the platform in recent years. So there's been a lot of attention spent on making the compiler faster, but also making the base class libraries work better with performance. Some of those are related to actually sort of fixing sort of algorithmic performance issues, but others are about reducing the amount of memory being used. And you can see that in some of the features that have come through over the last couple of years. So C#, when C# got tuples as part of the language, they didn't use the existing system.tuple type. They introduced a new type, system.valuetuple. So system.tuple, which has been around for years and years, is a class. Excuse me, and using that introduces a whole load of allocations, and will then again sort of a lot of use to that will lead to more garbage collections. Whereas you can use value tuple and you can avoid that kind of situation. A similar thing then with the async enumerator, which is the await for each feature, and also the value task. The work with value tasks there, so you can actually use a value type to represent tasks now, which again avoids unnecessary allocations. And more specifically as well is the span of T work, and we'll have a look at that as we go through. All right, so if we want to avoid too many allocations, then let's have a look at some of what I call the low-hanging fruit, some of the things which are easy to fix and easy to find and easy to fix. Then we've got a handful of these there. We'll just have a quick look at that through this. So you might be familiar with some of these as they are sort of standard techniques then for sort of improving your memory usage. You've got things like object reuse. So if you've got an existing array, you want to sort of rather than throwing that one away for garbage collection and then allocating a new one, you can reuse that array. You can pool it and get an object from a pool, reuse that object and put it back into the pool there. So you're saving your allocations there by reusing already existing objects. A similar thing can be done with string concatenation. Every time you concatenate strings together, you're creating another string. If you're doing that several times just to create one string, you end up creating a whole load of strings just for one at the end. So use string builder. It's an obvious one there. And again, if you're using a string builder, you can create a pool of those. So you can reuse those string builders as well. And so that string builder then can just have a single allocation for the length of the string. And if you already know the length of the string, you can pre-allocate that as well. So instead of having the string builder having to create and extend the internal memory as it goes. PARAMS arguments is a good one as well. It's an interesting one here because this is actually kind of a different type of allocation here. This is a compiler generated allocation. So this is an allocation which is not explicit. You don't see it, but the compiler is doing it for you. So on the left here, we've got a params method, which is taking in a string array of arguments and doing something with it. When we call it with, say, 2 arguments there, just type quite nicely the two arguments. But what the compiler is doing over on the right-hand side is allocating an array and passing that array in. What's really interesting is when we're calling the method with no arguments, there's still an allocation happening here. The compiler will add an allocation to an empty string, an empty string array. So even with our code, when it looks like we're not passing anything, we're still paying for an allocation. Except that's not quite true. And this is where you shouldn't trust me again. I'm just a guy with a PowerPoint. You don't necessarily believe everything I'm saying here, because newer frameworks and compilers have changed this behavior. And instead of having an empty array allocation for every single method call, you get to reuse the array.empty type and method. And so that gets rid of that overhead of that allocations going on there. So again, just to make sure this message is emphasized, make sure you're measuring here. Don't necessarily trust the things I'm saying here, and your situation is also going to be different. For example, if you call this method once in the lifetime of the application, it doesn't matter if it allocates an array or not. It's not a big deal. But if you're doing it inside a busy loop, then it can matter it can be much more important. All right, let's go back to that list of things we could do to fix things up. Boxing. Boxing is another source of allocations that happen. The boxing is when we pass a value type to a method that expects a reference type. So if we want to pass, say, an integer where the method is expecting an object, what happens here is that the runtime will create a new object on the heap, the box for us. That contains a copy of the value type, and when it's used, it's unboxed and used in just as normal. But one of the key things here is that any changes to the box value doesn't affect the original. What you can see here as well is the little screenshot here of a plugin which we've got for ReSharper and Rider called HEAP Allocation Viewer. And this will highlight when you have boxing allocations. So for example, console.writeLine, it's expecting object values to be passed in, which it can be used as arguments to the format string. But these are objects, and we're trying to pass in an int. And so that's going to get boxed for us immediately. And so there's an allocation there that we perhaps might not be aware of. And again, if that's just happening once in your application, that's not a big deal. But if it's in a tight loop, busy loop, that might actually affect some of your performance over time. Right, but let's step back a little bit, though, because I've been talking about reference types and value types. So let's just kind of remember what those mean. Now, what's the difference between the two? So a reference type is a type that's defined with the class keyword, while a value type is defined with a struct keyword. Reference types are allocated on the heap, while value types are allocated on the stack. They can also be embedded inside a reference object. So for example, if I have a person class, that's going to live on the heap. But a person class can contain, say, the age of a person. The age is going to be an int, which is a value type. And so that's actually going to be embedded inside our reference object there. So value types can live on the stack, or they can live inside an existing object. If we have a variable for a reference type, it's actually a reference to the thing on the heap. So if we've got a variable here, it's actually it's pointing to, telling us that the actual person object is on the heap. Whereas if we have a variable for the value type, that's the value itself. So an integer is just an integer. It's not telling us that the integer lives somewhere else. Same with a 3D point. If we have an x, y, and a z, float values of each there, they're not copied somewhere else there. The actual 3D point is the object itself, is the value itself. If we are passing around a reference type, that's passed around by reference. So if we've got a reference and we pass that to another method, they both still point to the object that lives on the heap. So we're passing things around by reference. But because a variable for a value type is the value itself, if we pass that around, then it's a copy of the value itself. So we're passing things around by value means things are copied. What's interesting is when you have assignments, because an assignment for a reference type is a copy of the reference, not the object itself. So again, if you have a variable and a variable, both of the same reference pointing to the same person, they point to the same instance of the person there. It doesn't copy the person object. It refers to it. They both have a reference to the same thing. Whereas if you have an assignment for a value type, such as a 3D point, it's actually a copy of that. And so you get a copy of the value itself. And this is interesting because that applies not just when you pass something into a method, but also within a method as well. If you have two variables of a value type in a method, then you've got two copies of the same value. And if you make a change to one, it doesn't affect the changes to the other. Okay, so heap and stack, I've already mentioned these now, so let's just refresh ourselves with what a heap and a stack is. The heap is general purpose memory, and the heap allocation can last for the lifetime of the application. Your person can live longer than the lifetime of a particular method. You can save it in a dictionary, you can look it up multiple times during the lifetime of an application, and it's always going to be there, and it's there until you have finished using it. The stack, on the other hand, is a block of memory for data which is required by a method. When you have a method, it kind of pushes more space onto the stack there for local variables. So you've got this space in your stack which you can use for local variables for that method. And when you finish your method, then that gets popped and the stack disappears there. The stack is returned to normal, and the space you have been using for your local variables is no longer there. So the stack allocation for the allocation lifetime for a stack is the lifetime of the method. So you can't have anything living on the stack which lasts longer than a method. Since value types are the whole data, if they are allocated in the stack, they live directly on the stack. The stack contains all the x, y, z of my 3D point. What you've also got with the stack is the stack alloc keyword. This allows you to create a block of memory on the stack. It's probably not used very often. I've never had to use it myself, but it's useful to know that it's there. So one of the key things with the stack is that both allocation and cleanup is cheap, but you've got limited space. So let's get back to our list of things that can cause us memory usage that we might want to avoid. And we look at closures. Closures is when you have a lambda which uses a variable from outside of its definition. So for example, here we've got a filter names method which has got a where link expression, and it's got a lambda which is capturing the name parameter there. And again, our heap allocation viewer plugin can highlight this for us, and it can tell us that we've got a capture of the name parameter. But where the sort of expense of this comes in is that the compiler rewrites this code, and it creates a new class which is going to contain the name parameter there as a field, and the lambda itself is now going to be a method on that class. And so you've got an extra allocation going on here to capture that information, to capture your closure information. And using link here as well is also fairly expensive. So link is a great way of writing code, of being able to write very expressive code. So it's very easy to understand and know exactly what's going on. But if you're not careful, it can be reasonably expensive. So you've got the closure, the expense of the closure itself, but also the implementation of where, for example, is a static method, an extension method, which is going to allocate an enumerator class, which you're going to use, and again, it adds to your allocations. And the heap allocation viewer can show us this. Next one on the list then is iterators. Iterators are very useful. We've got the yield return keyword here. It allows us to generate a sequence of items and work with them in a very nice sort of concise manner. Again, it's nice language syntax for working with this kind of thing. But again, what happens is the compiler rewrites everything here, rewrites into a state machine, and then there's allocations involved there for allocating the state and maintaining that state. Async await has a kind of similar issue in that code gets rewritten into a state machine here, and there's allocations for the state machine, but there's also extra allocations for things like the task method builder and for the task or task of T that you return back. So every time you have a return, you allocate a task of T which contains that return. This can be expensive for some common use cases. So for example, if you have a method which is sometimes asynchronous but usually synchronous, then basically every time you are returning something, you're allocating. But if it's a synchronous return, you're allocating essentially for no reason. You're just creating a wrapper class to return back a value you already know. Similarly, with the way that tasks work is that you don't get much reuse of that class once it's been returned back with a result in there, and so on. So there are expensive issues involved with this. Now, one of the things you can do here is use value task, and this is a new type which, well, it's not that new now actually, but this is a type which is a value type and which can fix some of these common use cases. So if you have a synchronous return, you can return back a value task which contains your result. And this avoids the extra heap allocations then on how to work. And there's an interesting link down the bottom there, which sort of explains in more detail of what a value task does, why and when you would want to use it. I've got a page with links at the end as well, so all of my links will be available at the end. All right, back to that list. So we've kind of been through those lists and we've seen how they can sort of add allocations. And again, they're not massive allocations, but doing it often enough can cause a lot of memory to be used without you necessarily appreciating it. And there are ways of mitigating this, of working with this and trying to avoid this. So we've already had a look at object reuse and string concatenation, but params, we can fix that by introducing overloads with a common number of arguments. So if we know that your method is usually called with 2 parameters, introduce an overload which has 2 parameters, or with, with 0, 1, 2, 3 parameters, and then the rest, the times when it gets called in, a few times with 4, 5, or 6 parameters, have those as params. Similarly, you can avoid the boxing allocations by using generic overloads. So if you have a method of t, then you can let the JIT compiler handle whether that's going to work for ints, value types, points, objects, person, whatever, and it can handle all that for you. Closures, you probably want to avoid those in a critical path. Again, if you're in a busy loop which is doing a lot of cycles on the same thing, don't put a closure in there because that can be that can just sort of add memory pressure into what's going on. So you can, instead of letting the compiler work to generate a class and allocate state, you can explicitly create state yourself. Pass that state in as an argument to the Lambda to avoid the allocations that the compiler would do. You should also have a look at local functions, a recent C# feature, because under certain circumstances, the local function will create the closure type as a struct. And so it'll use a value type to represent the closure information there. So you get all the benefit of the closure and the nice syntax, but it's actually not going to allocate anything on the heap for you. And that can be really useful. Similar advice, really, if you're going to be using link, avoid that in a critical path. You can get a lot of the way of link with using for each and if. It might not be as nice code. The code might not be as expressive and as terse, and it might be slightly more verbose, but you can then avoid allocations doing it that way. Iterators is an interesting one because there's no really good advice on how to avoid that there. Perhaps you should return a collection, but then if you allocate a collection, you're still allocating. And so you also lose the benefits there of having a lazy evaluation of the sequence there. Do you want to return a large collection, but only use some of it? Or do you want to have a lazy evaluation so you can stop evaluating when you're done? So there's no real straightforward advice on how to avoid iterators, but it's a good one to be aware of the cost and to use that then to measure and to profile and to see whether it affects your particular application and usage. And async await, as we mentioned there, you investigate using value task. So those are our kind of easy things that we can know about and how we can fix with them. I want to move on and have a look at something a little bit more interesting there and have a look at reference semantics with value types, which is a bit of a mouthful, to be perfectly honest. It's a bit of a strong sentence there, which is tricky to understand. And so what do we mean by this? It's a bunch of features, really, that came through in C#7 and some of the minor releases that followed. And it's these sort of 5 or 6 features put together there give us a whole lot of useful things we can do. So we've got things like in parameters, ref local and ref return, ref read-only return, a read-only struct, and a ref struct. These are really useful kinds of things, and we'll have a look at those. But before we do, what do I mean by this? What does reference semantics with value types even mean? So the idea here is if we are using a reference type, allocating that has a cost in terms of garbage collection and perhaps affecting your memory usage. But passing it around is cheap. I can pass things around by reference, and it's very cheap and easy to pass them around. Allocating a value type is cheap, on the other hand, because it just lives on the stack and it gets cleaned up very easily, and it doesn't add to your garbage collection budget, as it were. But passing it around has a cost, because I have to copy things. If I want to modify it, I have to wrap it in a box, and that is another allocation. So why can't it be both cheap to allocate and cheap to pass around? And that's exactly what reference semantics with value types does. It basically allows us to use value types in the same way that we can use reference types. So we can pass by reference everywhere. So we can reduce the number of allocations we have, or rather reduce the number of heap allocations we have, which allows us to reduce memory traffic and therefore reduce the number of garbage collections. And that gives us much better throughput and a much better responsive system. We can also then pass by reference, and that allows us to avoid our copies. And the sort of the allocating on the stack, the extra allocations on the stack, allows us to modify things and basically work with references that are cheaper, basically. It is again important to point out that this is a whole load of very low-level optimizations. They are micro-optimizations. They will be used in the platform, though. So again, getting back to that point of knowing what your platform does, then this is part of it, because you're going to be building on things which use this information. So it's going to be used in the platform, but it's also going to be used in critical scenarios such as games or file parsing, for example, parsing the headers from a HTTP request or parsing in a JSON file, also for serialization, for trying to write things out, and also for lots of other features as well. And before you know it, actually, there's a lot of useful things that are going to be happening here. If you're working on something that is performance critical, some of these things can be really important. All right, so I have been talking about pass by reference and pass by value. Let's have another sort of refresher there as to what I mean by that. If we have a variable for a reference type, it's a reference to the actual object on the heap. Passing a reference type to a method is just passing the reference. The caller and the called method see the same object on the heap. That's fine. That's nice and straightforward and easy. The object lives on the heap, and we've just basically telling the method where it is on the heap and so how to use it. A variable for a value type is the value itself. So again, if you think about my 3D point, we've got an X, Y, and a Z float values. Those are all stored as the actual value, and they are not kept on the heap there. Passing that value type to a method copies the value. So I'm not giving any kind of reference because there's nothing on the heap to give it a reference to. But so I have to give a copy of the value. If I am assigning a value type to a new variable, that also copies the value. So we can end up with two copies of the value within the same method. And if I change that copy, the original value is unmodified. If I pass a value into a method, the original value is unmodified. So there are sort of side effects and a lack of side effects, funnily enough, around value types. It's also important to point out that these copies aren't actually that expensive. Again, if I'm talking a 3D point, it's 3 float values. That's not that expensive. Copying that around on the stack is actually not that expensive, but again, we want to avoid them if possible because we've got limited space on the stack. So the first feature in C#7 that I want to have a look at is ref return. This allows us to return back a reference to a value type rather than a copy of the value. So this means that I could get something back into my called method, and I can modify it and modify the original value rather than modifying a copy of it. So ref return allows us to return back a reference to the value type, and it's important to point out here that the return type of the method changes. So if you have a look at it in IL, in a decompiler, in a disassembler, you would actually see that the return type of the method for, say, returning back an integer reference is not int, but it's an int reference. So the return type is actually different. So there are important implications of this. The lifetime of the return value must exceed the lifetime of the called method. If you are returning back a reference to something, that something must live longer than the method, because if it was in the stack of the method, that stack has just got cleaned up and it's gone. So you can't have a reference to something that doesn't exist anymore. So it must return back a reference to a field or to something that was passed into the method in the first place. You can't return back a reference to a variable in the method that has just finished. There's also implications there with things like async methods, which have got rewritten into the state machines, for example, there. So they're not allowed in those situations either. Modifying the reference you get back from a ref return is the same as modifying the original value, because it is the original value. You've got a reference to the original value. So you don't have a copy anymore, you've got the original value, and if you change it, you're changing the original value. There's a lot of interesting things you can do with this. So for example, you could return back a reference to an array element and update it in place, rather than having to return back a copy of an array element. So if I had an array of points, what I would normally have to do is return back the point, do some modifications to it, and then set that value back into my array. Whereas if I'm using ref returns, I can actually return back a reference to the array element, modify it. Because it's the actual value itself, I'm modifying the value in the array. So I can do a whole lot of useful things with that. When you're using this, you have to use the ref modifier on the method declaration in the return type, and you also have to use it in the return statement as well. But we've got a small problem here. If the return type of the method has changed, we now have got an int reference as the return type. How do we use it in the calling method? So how do we store the return value of a ref local? We can't assign a ref return to a new variable because that'll create a copy of it. So any variable we've got, if I say I have my int, that's an int rather than int reference. And so if I can't assign an int reference to an int, that would make a copy. So what can I do with that? And that's what the next feature, the ref local, allows us to do. It allows us to have a variable which is a reference to a value type. So I can have a ref local variable which is my int reference type. And so accessing that variable accesses the original value there, and we can work with that just as we would normally. One thing to point out here is that the type inferencing with var, if we use the var keyword to get type inferencing there, we actually get the value type, not the reference value type. So you have to use the ref var combination of keywords there to get it working as you would expect. That can be a little bit of a gotcha there, and so you kind of need to be a little bit careful with that one. Okay, so let's have a quick look at some code. If I can get to, there we go. So this is Rider here, and I've got some examples of what I'm talking about with some of this code here. So we'll have a look at something that demonstrates ref return and ref local. I have a struct here, which is a point. It's a simple XY value. I've got my X and Y float values. They are public, they're fields. They could just get modified if necessary. It's a simple point struct value type. I've now got an enemy class which has a point, and so I can set the point in my constructor here, and it will then get stored as a local field, as a field, and that is a value type. So that field is actually embedded directly inside the enemy class instance. I have two methods. One which is just going to get me the location and return back a point, just as you would normally and how you'd expect. Return type is a point, and I just call return location. The other method is returning back by reference. And so I've got, you can see here in the method declaration, my return type is ref point. And when I'm actually trying to return something from it, I have to use the return ref keyword there. Now I have some tests here. So we're going to assert that the behavior does what we expect it to do, and works as we'd expect. So the first one is if we call enemy get location, this is just going to return a simple point. And I've got my point there, point location, and I can set that, because it's just a public field, I can set that value to the X value to 12. I can assert that that's the case, but that's working with a copy. So I've returned back a struct a value type. By returning a value type, I return back a copy of the value itself. So if I call getLocation again and assert, we can see that the value has actually changed. So let's try using the getLocation by ref. I'll run these in a minute and we can see that these are all true. If we have this getLocation by ref method here, then I should be returning back a reference to my points. But I'm assigning it to a point here. And so that's actually going to be another copy as well. And so I can say, I can change it and I can assert that that value has actually been changed. But if I try it again, I see that I didn't change the original value, even though it was returned by ref, because I assigned it to a value type rather than a reference to a value type, then it was a copy. So what we actually want to do is use the ref keyword. And just to show you here, just to show the point here, if you use var copy there, that's not a reference type there. Var is not a reference, var is the actual value type itself there. So that it ends up being a copy. What we have to do is use ref var on a location as well. And then we get a location which we can change the value to. And then if we assert that down here, then we see that it has actually changed. So let's just quickly run all of those tests. So if I Alt Enter and hit run all, that will quickly go through and we get green tests. So all of those things that we've asserted, they're all true and things work as we'd expect them to do. Now there's one extra test down here. This is a bit weird. One of the really strange things about being able to return back a ref return value is that you can actually now use a method as the left-hand side of an assignment. So you can actually do something like this, which basically hurts my head. And please don't write code like this, because that's just asking for trouble. But it does work. Incidentally, it does work there. We're returning back the reference to a point. We're setting it to be a new point, and it has actually updated the value there. Okay. So next feature then. Let's just check. Yeah, okay, so the next thing then is a ref read-only return. So this is great. We're now able to return back a reference to an existing value type and modify it. So I can modify my point. I'm not making any copies unless I want to. And I've got the ability now to return back a reference, get the original value, and I can modify the original value. But this could introduce strange and weird bugs. So let's stick with my point here. Let's say we've got a 3D point, and if I return back a reference to that 3D point, which is representing the origin of my entire coordinate system, 0, 0, 0, if I return that back as a reference, anybody could change that, and all of a sudden my my origin point has moved. And that could break a whole bunch of things and cause very difficult to find problems. So we want to be able to return back a reference to the original instance for the benefits of the reference usage there, but forbid the caller to modify it. And that's what a ref read-only return does. So what happens here is that you have a type. So when you declare a variable, instead of using the ref var keyword, you actually use ref read-only var, and that will then indicate to the compiler that this is going to be read-only, and you get a copy of it. Sorry, you get a reference to the original value, but if you try and do anything with that, then the compiler will make a defensive copy for you. So there'll be copies made, but you won't necessarily see them happening. So let's swap back to where are we? There. Let's swap back to our code, and we can sort of show this in a bit more example, because it's a little bit hard to see that just from the text there. So again, I've got a second version of my point value type there. It's a struct. I've got public X and Y, so they are modifiable. And I have constructor to create it. Now I've got a new method here called translate in place. This will mutate the struct. It'll change the struct there. So I can say move this point 10 units to the X and 10 to the Y, and it'll just update its own fields and update that. So now we have a couple of different ways of representing this there. So I've got my static method here, which represents the origin at 0, 0, and I can get a hold of it now by reference and work with it. Now, the idea, look, this is a reference here, so this is going to be dangerous. So I can get a reference to the original value and modify it and move the origin. Alternatively, I can create a read-only point here and have a property. So it is important to point out as well, yes, so I've got a property there. I'm using the shorthand syntax, but it works just as well with the longer syntax as well. So you can have it so that you've got a ref read-only point there. So I'm declaring this, that when I return it back, then you're not allowed to make any modifications to this value. And so we do return ref, we get back our reference to the value. So the first thing we want to say about this then is that we have, we call our point.origin, which was the receiving the copy. This isn't by reference. We can't modify it. If I change the value there, then I don't modify the actual origin value there. So this one is safe, but it's making a copy. So I'm not getting any reference semantics, but I'm getting a copy instead. Let's use the ref var version instead. This is a non-read-only version. So I'm actually getting the original value of origin, the actual value, the real value, and I can change it. And when I do change it, I change it in the for everybody, basically. So what we want to be able to do then is have this ref read-only var. So we're getting a few more keywords put in here. We call this read-only origin. We're calling it by ref, so we're getting everything as a reference value. If I try and change that value, I actually get a compiler error. So even though that X there is a public field, and I can modify it quite happily here, the compiler doesn't like it because it tells me that I've got a read-only variable. It's actually got a bit more of an interesting description there. You cannot modify a struct member when access struct is not classified as a variable. So by using this ref read-only var, it's not actually a variable, it's a reference to an existing bit of data. So let's just, where's undo gone? There we go, undo that. So that's compiler. I can't change anything, so obviously those tests are going to be fine. What happens when I call a method though? I've got my translate in place. So if I have my ref read-only var, I've got this method, I've got this origin, which is the actual value. It's not a copy, it's a reference to the actual read-only value. What happens when I call translate in place? This is going to change its own value. So surely I would be able to change the origin by calling a method. And as it happens, this is where the compiler steps in and builds a defensive copy. You're calling a method on this this reference, but the compiler doesn't know what this method is going to do. So it assumes the worst, it assumes that bad things are going to happen, and it assumes that it's going to change something. You've said it's read-only, so it says, fine, I'm going to make a defensive copy here, and you're going to call it on a copy. So I can call translate in place, and that will change the value. But if I assert the actual values that are stored, they're still 0 because it happened on a defensive copy. And Ryder's giving us a message here as well to say that a possibly impure struct method called on a read-only variable, the struct value is always copied before invocation. So by possibly impure method, that means that the method might change the state of the actual variable itself, the actual value type itself, which is true. Right, and that's just one, that's a method to make sure that everything gets reset between times. So let's just run all of those and check that all of our assertions are true. And we're still green, so yep, that's all true and everything is as we expect it to be. All right, so that's kind of return values, and that's very useful there because we can now get a return value as a reference. We can modify it if we want to, or we can have it read-only if we want to. What about passing things into a method here? Well, we've now got in parameters as well. So you might already be familiar with an out parameter or a ref parameter. Out parameter is a value that comes out of a method and has to be initialized inside the method. Ref is something that can go in and out. Ref is for, I can use that with value types, and I can pass something by reference with ref. But if I pass a value type in with ref, then I can modify it. So I can pass in my point 3D, excuse me, I can pass in my point as a ref parameter here, and I can modify it inside the method itself. So what we've now got is something which kind of complements all of those. We've got in, out, and ref now, and in is a value type passed by reference, and once inside the method cannot modify the original value. So again, the compiler will enforce this by creating a defensive copy for us. And let's just jump over to some more code, and we'll see. And we have another point here, and this is a mutable point. The idea here is, of course, we've got mutable values there. We've got a couple of floats which are public. We create them in a constructor, and again we have our translate in place method, which will change the state of the actual object itself, of the struct itself. So just to prove that that's the case, we can say we've got a method will mutate its own state. So if I create a point there at 10, 10, and then I call translate 20, 0, then I can assert there that it's actually moved the point. The point is now at 30, whatever it was before, 30, 10. Oh, no, sorry, yeah, 30, 10, because it didn't change anything, it was 0. Now, if I uncomment this one, and I've got it passed in as an in parameter, I can't call the I can't set the value of the field there, even though the field itself is a public field and it's writable. I can change it. I get a warning. I get an error here to tell me that I can't modify the struct member when the access struct is not classified as a variable. Basically, it's telling me this is a reference. This is a read-only reference. You can't change it. Now, I don't get a compiler error here, so the colors are a bit tricky there, but that one's an error. So this is an error here, and this is a warning. And we've got the similar warning as we had before to tell us that the possibly impure method is called on a read-only variable. So in that case, the compiler will generate a defensive copy for us and stop us from doing it. So it works, it'll compile and it'll do something, but it's possibly not doing what you expect it to. At the end of this, point is not going to be changed. I think I can undo that. Okay, so the next thing we want to sort of assert is calling a method doTranslate here. So let's pass it into an in parameter. Obviously, I can't use the in parameter on the test itself, so I create an instance. I pass it as an in parameter to do the work, and then I assert that nothing has changed, even though it was passed as a reference type, but as a read-only reference type. And again, we get the warning here, same warning we've just seen there. It's going to be calling this on a copy, so no changes are made, and we can assert that no changes were made. Now we could try and cheat here. We've got a reference parameter here. We've got a value type here. What happens if we try and pass it through as a reference? So we could pass it through as a reference parameter, which should be read and write. I should be able to pass it in, so modify it completely. And if you see here, we don't have the warning anymore for translate in place down here, because it's now working on a ref of a ref parameter rather than an in parameter, and we can then sort of assert then that that's not the case. But then if we go back to the calling point, we can see now actually that there's an error. The compiler doesn't let us do this. It understands that we're trying to cheat and we're trying to pass an in parameter as a ref, and it doesn't let us do that. So we can't do that. I can't even compile. Okay, so let's just assert that. Oh, hello. Okay, and if I just run those tests, we should get green again. Yep, so everything we've said there is true and holds true. And let's have a look at the next bit. Okay, so we've got read-only struct. This is great. So we've got an in parameter and a ref read-only can create defensive copies. How do we fix this whole thing about the defensive copy? That defensive copy can be tricky because we're going to do something and we think it's going to make a change to the struct, but it doesn't modify anything. The compiler throws it away. It calls it on a different instance, and we lose that state. We lose that change of state. What you can do instead here is say, don't call something on a defensive copy, but call it completely, you can tell the compiler that you're expecting that all of your methods are going to be pure, not impure. All of your methods, sorry, none of your methods are going to change the state of the object. And you do that using a read-only struct. So the compiler enforces then that all fields and properties are read-only. The whole thing is immutable, and basically we can't make any changes there. This gives us something which is more efficient. No more copies are made when calling the members there. And again, micro-optimization. Very quickly, we can see this in action here. I've got a read-only struct. I've got a read-only struct. There are my keywords there. I've now got my fields are read-only. If I delete the read-only there, I get shouted at. The compiler tells me that this isn't correct. You can't have that. So I need to have my read-only keywords. And so now if I try and have my my method that changes the state, it's going to fail. Of course it'll fail because I got read-only fields. I can't make any changes there. And I get warnings and errors here to tell me that you can't modify anything. So that's not going to work. And again, I can return things back as ref read-only, and basically now I'm sorted. So I'm fixed. So if we get calling things by origin there, then we've kind of got a copy, but we can't do anything dangerous to it anyway because it's immutable. So even though I got public fields, I can't change them because they're read-only. So that's a compiler error. And then if I try and get something back as a ref read-only field, then again I get a compiler error because I can't modify something which is not a proper, which is, I can't modify it because it is a ref read-only reference, and I can't call my method on that because it doesn't exist, because I can't write that method. So this is great. Basically the compiler is enforcing a whole load of things for us, and I can run those tests, but it's pointless because basically everything is a compiler error, and so I can't do anything around that. So that is pretty much all of the features that sort of C#7 added for reference semantics for value types. And the big thing with this really is that there's no changes to the CLR. So it doesn't need anything in the CLR to actually change. This was always there, always available. You just didn't have the ability to write the C# for it. So there's one last thing with the reference semantics in C#7, and that is ref struct. This is a bit weird when you first hear about it. This is the way to declare a value type that can only be allocated on the stack. So it can never be part of a reference type. So if I create, say, a point, which is as a ref struct, I can't put a point inside an enemy class. Ref struct does not allow me to do that. So this kind of has some very specific constraints to it. So that means it constrains the lifetime of this particular struct to the calling method. So it can't be boxed, it can't be used inside another struct or reference type, and it can only exist basically in the lifetime of the calling method. So there are very, very limited use cases for this. So you can use this when you're working with stack alloc memory. So if you're allocating something just to sit on the stack, you can put it in there if you want to. But the main reason for this then is for span of t. And so we'll have a look at that now. So we'll move on to that. Span of t is a fairly new type, which is there to unify working with any big block of memory, contiguous solid block of memory there. So things like arrays and strings and native memory and stack allocated and stuff. It's also very, very useful for working with segments of memory as well. So I can work with a whole array, or I could work with just a small section of an array. Same with strings. It allows me to very efficiently work with substrings. And it provides a sort of like an array-like indexer API for that as well. So I can just use square brackets 0, square brackets 10, whatever, to work with that. There's also a read-only span, which provides a getter index only, so I can't set the values, I can only get the values. And it's type safe as well. So because it's span of t, each element is of type t, and I can get the values and work with them in a properly type safe manner. It also has array-like performance. It's not quite the same as array-like, but it's very, very close. And the more recent runtimes have special support to make this work as well. So the key thing with span note is the ability to do slicing. You can create a new span based on a subsection of an existing span, so without allocations there. So I can create an array. So if I have an array, I can then create a new array which is part of that array, and there's no allocations there at all. So I've just got my one array, and it references a piece of memory inside that array, which is really, really useful. It's particularly good for things like parsing. So if I have a single string which represents a JSON document, I can parse that very, very easily and work with substrings of that without any allocations at all. So the implementation is fairly straightforward. It's a value type, which means it's a struct. On older versions of the runtime, so .NET Standard 1.1 and .NET Framework 4.5, you get it from the system.memory package. And it introduces a bunch of new APIs and overloads for the base class library as well. So things like string.asSpan, so you can get something as a span, and then stream.readAsync can return you back spans and so on. So there's a huge amount of work of all of the stuff we've just been talking about, the reference semantics in the base class library there. So you can do a whole bunch of things there, allocation free. And so you've got span of T, read-only span of T, and also memory of T as well. So I'm not going to go into that one today, but that's something to look into as something which kind of relates to all of this there. There are two versions of the implementation. There's a portable version and a fast version. The fast one is for modern runtimes, which have got the support built in. Portable doesn't mean slow. It just means that it's not implemented, it doesn't have specific support in the runtime. It works on the older versions of the runtime, .NET Standard 1.1 and above, .NET Framework 4.5. It's not as fast as arrays, but it's not slow. This struct has three fields: the object reference, so the reference to the big array, the offset within the array, and then the length as well. So that's something which is then slightly larger than a faster version. Dereferencing it is slightly more complex because you have to go there, move along, and work with it there. The fast implementation, as it were, requires runtime support. It's for .NET Core 2.1 and above. Of course, we're on .NET 3.1 now. 5 is just around the corner, and all of this now is built in to the runtime. It's only got two fields, what's called a by ref internal pointer. So again, if you've got my array, I have a pointer which is pointing directly inside my array. So I don't have to point to there and have an offset. I can point straight there and have a length. And so that's all it needs to keep. Slightly smaller than a struct, and accessing the data is slightly simpler. But again, it is useful. The runtime has got some specific optimizations in there, so the JIT understands this type, and so it can do things like array, like it does with arrays, and sort of get rid of some of the bounds checking in a loop, and just make the accessing a whole lot better. It recognizes the type, and it can work with a type properly, and you've basically got the same performance as arrays. So what does this have to do with ref struct that we just mentioned about? Because we've got two fields or three fields, we need to update those fields atomically, all at the same time there. If we kind of did that just as a thread was switching, we would break things and it would all go horribly wrong. We can't put a lock around it because the whole point of span of T is for performance. And so we kind of need to have something that only works in one place. These internal pointers, being able to point directly to the part of the memory that you want, is an expensive thing. Having too many of those at any one time is hard for the garbage collection to keep a track of. And there's then, if you're going to be using span of T to represent stack allocated memory, how do you do that if span of T is living on the heap? Because of course the stack could disappear at any time. So the solution is that span of T is a ref struct. And so all of those limitations of the ref struct are exactly what can help the span of T work with all of this. So because it can only live on the stack, only one thread can access it at a time, so we don't have to worry about thread safety, and it's got a lifetime constraint to a method call. So again, we can work with stack allocated stack space there, and because we can only have a limited number of those, we don't overload the garbage collector with these pointer tracking, with the pointer tracking. So very quickly, have a quick look at span of T. We have some data which we're going to use here. We've got a string, which just says hello world, and we've got an array of 10 numbers here. So we can get a string as a read-only string. So we can use this mystring.asSpan. This gives us now a read-only span of characters. And then I can just assert, I've now, with this read-only span, I've now got extension methods and properties and things that I can use to work with that as I would do with a string. So I can say, get the length of the string and compare it against the length of the span. I can do span.equals against a string, and this will now do a string comparison against a span without having to turn that span into another string. And I can do something like, starts with as well. So I've got a similar API for working with a span, which acts like a string as I do with strings themselves. I can then use substrings as well. So I can use this slice method to get me a slice of my original string here. So I'm going to get a slice starting at index 6 and going to the end of the slice itself. And there I can just assert that that's true there. I can assert that it's the right length, that it's equals. Again, I'm doing a sort of string comparison here against a span, which is useful. And then with things like numbers and arrays, I can get a span rather than a read-only span. I get a mutable span, and I can get a subsection of those. I can write into my subsection, and then I can assert it that value itself has changed. And so if I just run those tests now, we should see that those are all green and that everything is good, and we're all green and nice. And now let's just undo this one here. The best thing about all of this is that everything I've done above, so these are the 3 tests that we've already got. I can run those again, and I can assert that there's no memory usage there at all. So I can say, get me my total memory usage right now, force a collection, and return me my total memory usage. I can tell the garbage collector to not do any garbage collection until I say carry on. And I can call my tests, and I can say carry on, and then I can assert the memory usage there is as it should be. It should be 0. And if we run that, we should hopefully now, as it recompiles and runs, we should have. We don't have a green test. This is sometimes flaky. This is not a good way of measuring. There we go. We've got a green test. So again, doing this a very crude way of checking to see whether you've got memory usage going on here doesn't always work. You are much better to use a proper profiler to do it, but this is a nice, quick, easy way to show that that works. Let's just try that one again. We should get a green again, hopefully. We get red. And we get green. So, okay, sometimes it works. Okay, so that's span of T, and it is, of course, very useful then for lots of things, being able to parse data without having to allocate substrings. So you can use the span of T API to get substrings without allocating. You can check against them, string equals type methods going on there, get the length of something without having to allocate any strings there. So it's going to be very, very useful for parsing, and also for things like working with sub-arrays and for using then reference semantics to be able to change the values in arrays without having to copy it out, change it, set it back again. You can actually just update the value in place. So there's a whole load of things you can go on there. And that brings me to the end of the presentation, really. I've got some links here which are useful there. Top right is the code which I've been using to run the tests there to make sure that everything works as expected. And then there are some really, really useful links going on here. The documentation for reference semantics with value types is great. It explains everything in a really good detail and explains how it works, why it works, and why you'd want to do it. And then there are several posts there about span of T. There's a video which kind of explains things. There's a really good post by Adam Sitnick. And then also details about the JIT itself and the optimizations that have been put in for span of T and how the compiler will recognize that and optimize working with span of T. And then the link which I had earlier on, which is about details about value task and why and when you would want to use value task instead of just using sort of task of T, for example. And so that brings me to the end. Thank you very much for listening. If you take anything away from this, please take it that you should profile your code before diving into some of these solutions here. And of course, if you have any questions, then please fire away. Other than that, thank you very much.
If you guys have any question, unmute yourself and to Matt. Matt, can you show us an example where we can profile, like what is the tool you use to profile? Like a simple example, is that okay, if that is possible right now?
Oh, I don't have anything set up right now to be able to show, unfortunately, but excuse me. So there are a couple of things you can do in Rider. We've got sort of tracing profiling, which you can use here. So you can use like the timeline profile to get a whole load of events. The support for profiling is actually much better on Windows. So Mono doesn't have great API for working with profilers. It's not as good as Windows. You get much richer information from Windows. So unfortunately, I'm on my Mac. So you can do a whole bunch of things on Windows, which you can't do on Mac, you can't do on Mono or on .NET Core. Things are starting to change and get better. You know, there's more APIs being added to .NET Core, which are cross-platform and which can provide that kind of information. But right now, if you want to do some proper profiling, your best bet is to go over to Windows. From there, then we've got, JetBrains has got tools like .trace and .memory. .memory is a great one for actually diving into, proper detail about what memory your code is using, and you can do, things like see how many instances of a particular object are in memory at any one time, how much memory that is using, see where they are allocated from, and you can also do sort of very simple analysis of your snapshot. That's the word. You can do some simple analysis of your snapshot to find issues, common issues. So, for example, WPF applications, it can find things like event handler subscriptions which haven't been unsubscribed, and it can then show you that these are going to be keeping things in memory longer than they should do. The other one we've got then is .trace, which is a performance profiling, but there are three different ways of working with .trace, and so some of them are kind of shown here. Really, we've got sampling, which is really about performance in sort of wall clock times. So how long something is taking. Same with tracing, but the timeline view is really good because that then sort of captures a whole load of events over a period of time, and the events it captures are not just about how long something is taking, but it also captures other events as well. And again, this is really good on Windows. So you've got ETW, the event tracing for Windows, which gives you a load of information such as allocations. And so you can then sort of query effectively and modify the filter. You can filter your snapshot then by memory usage and also by things like subsystems. Well, how much memory is being used in collections, how much memory is being used in, so collections like a list or set and so on, but how much memory is being used in input output, or how much memory is being used in, link queries, things like, how much time is spent in garbage collection and so on. So the timeline view is very, very good. It's not just about performance profiling. It can also give you memory stuff as well. And when you see how much memory is being allocated over the timeline there, you can then sort of click on that and it'll show you then which methods are taking up or allocating the most memory, and use that as a way to then sort of dive into your code to see which methods you should be looking at to fix first. There's another thing with the debugger. I can't remember if this works in Mono. Let's have a look. So if I go into the debugger, there is a memory view, which will give you kind of like a fairly simple. Yes, we've got a memory view here. If I type string now, then we can sort of see how many instances of the objects are in memory at any one time. So this is not some. It's not so much a tool for profiling as such, because I can't necessarily find out whether, I've got 1,567 strings there. I don't know if that's good or bad. I just know that that's how many I've got in there. But what is useful is that you can use that then for things like differences there. So you can see we've got a diff column here. So I can actually then go to another breakpoint and then sort of compare the two and see how things are working. So that's a very useful tool as well. Let me just see if this will give me anything useful. So the timeline profiling, no, so that one hasn't given me anything useful in this instance. But the timeline profiling, I've got something there for, let's just see what this gives us. This is an old snapshot. Okay, so this gives you a bit of an idea. So again, on Windows, this is richer, but this particular one is useful because I've got a timeline allocation of. So I've got a timeline snapshot here of. It said unit tests there. So when was this? This was. Yeah, this was several months ago. So I've just had this lying around, and looking at it, it looks like some internal code for Rider itself to do with the Unity support, actually. So it was a bit of code I was doing to do some actual profiling, and this is the timeline view where you can then sort of decide on, have a look into see where there are issues. So I could see things like, okay, how much time was spent doing in collections, and this will show me, again, this will show me how much time was spent in. If I go down far enough, it should probably show me how much time was spent in collections such as lists and sets and so on. Or I can show things like, what I was doing for garbage collecting, waiting for garbage collection. And then under events, then I've got, again, garbage collection, exceptions it can show me. So where were all the exceptions happening? And I can also see then memory allocations. I can see that nearly a gigabyte of data was allocated during this process, whatever it was I was doing. And I can actually now see where all that memory is being used. And I've got this test gen maths, whatever that method is doing, that's used 330 megabytes. And I can use that then to sort of drill in to walk down there to sort of see eventually what was using up all the memory. So initializing a solution there, whatever that is actually allocating 300 megabytes. And it's like, well, okay, perhaps initializing the solution should be really cheap. Why is it allocating 300 megabytes? And I can then sort of navigate in there to sort of see quite what's going on. Whereas on the Windows viewer for all this will give me much richer information and show me what's going on there. So does that help at all?
Yes, man. Yeah, it was helpful. So basically, if you want to do some performance analysis, it's better to use Windows rather than the Mac, right?
Yes, in my view, yes. So
okay,
you get some information from the Mac, and so we've got profiling information in Rider itself. There, the user interface is more basic in Rider, so you can get a lot of information, but what you really want to be able to do is then open up that snapshot in .trace itself, and you'll have a lot more features and filters and things you can do then to kind of get at that. So if I want to do proper profiling, I will swap to Mac. I will swap to Windows.
Okay. So I have one more question. You gave us a slide on talking about a code, right? Like names.var name equal to name where you got it as a parameter, and you said you shouldn't be writing that way. You want us to write in a for each, or can you go to that slide?
Which one do you mean? Sorry, the
yeah
slide of what?
This
for link was it?
No. Yeah, go down.
Yeah, that one I think.
Yeah, yes. So you want us this to
So again, the answer is it depends. So
okay.
If you're, so you want to measure this first, and that's kind of the important thing. Is I'm not saying this is bad. I'm saying this is a source of allocations. So you're going to get an allocation using a link query like this, where you've got
Okay.
the where method and a lambda which has got a closure. You've got an allocation here, so that's not a bad thing. You know, if you call this once, twice, 10 times, that's not going to be a problem at all. If you've got a busy loop which needs to work really quickly, if you're doing it 10,000 times, don't do this. So if you're doing 10,000 times, you've now got 10,000 allocations plus 10,000 method calls. Well, in fact, you've probably now got the method call to where, the method call to next, the method call to the lambda itself 10,000 times. So there you've possibly now got 30,000 method calls. Whereas what you could do is have a for each and an if statement, and that's just, you know, one loop of code. Yeah. Yeah. So it all does depend. So this code can be absolutely fine. I write this code, you know, I write like this, and generally speaking, it's fine. But if you are doing something which is really, really busy, then you want to profile and see if it's a problem. If it, as I say, if you're doing a loop 10,000 or a million times, you probably want to do something different.
Makes sense.
Yeah.
Okay. Okay. I think I'm done with my questions. If you guys have any questions, please fire away with Matt. We'll wait for a minute, and then if it's not the case, how can we reach you, Matt? If there are any questions.
Sure. Well, up on the slide there, I mean, that's me on Twitter. If you're on Twitter, you can do Citizen Matt on Twitter, or you can email me, and I forgot to put my email address on there, matt@jetbrains.com. It's nice and easy.
All right.
Anybody else with any questions? We were all happy. That means I've explained everything perfectly, and nobody is really confused by reference semantics and value types.
I have a question about data slides specifically. Do you have a HEAP allocation viewer that you prefer or do you use? Or is one include also in Rider?
So there's a plugin for Rider. So if you go to plugins, I don't think I've got it installed as it happens, under HEAP allocation viewers, you can then just install a plugin, and once it reloads, then it will it'll show you those kind of highlights there. Excuse me. So if you've got Rider or ReSharper, it's the same plugin, and it will then kind of show you those highlights in the code itself. I'm not quite sure what it'll show in this instance, probably not much. But if you do, I mean, it can show things like boxing. So if I, where are we? Yeah, so if I create, point, and then try and pass, oh no, it's called copy. There, it should, why? It doesn't like me using that inside a unit test. But there we go. So now we've got, you can see there's a highlight of copy there because there's a boxing allocation going on. It knows that point is a value type, and then it can say you're converting that from a point to an object, and you're boxing it around. And so if we had our own method, void, whatever, which took in an object, and if I called whatever with copy, it'll, again, it knows that I'm passing a value type to an object there, and it tells me there's a boxing allocation going on. I could change that to be a generic method, and now it's gone, because the JIT compiler and the compilers will basically fix that all up for me.
Okay, thank you. I have another question about the iteration and timeline that is only used for unit testing or also for running all your code in general?
Oh yeah, absolutely. So the integration which we have with the tracing in Rider is based around your code here. So in fact, have we got it? Okay, rather forget about it. Short answer is no, you can run it on anything. So you can create a new configuration here based on these kinds of values there. So if we've got a tracing one, wait, where am I? Oh, yeah, okay. Right. So the idea is that we can run on anything. So when you're on Windows, for example, you can open up the .trace application, give it some command line parameters, and it just starts and runs, and everything is okay and fine. It'll trace anything. We've also got integration inside the IDEs. So ReSharper and Rider will be able to run and profile from a unit test, because that might be a useful way for you to start the particular process that you want to do it. In Rider as well, the way it works here is you can create a new configuration for creating like an executable to run something, I don't know, thing.exe, and you create a normal configuration for running and debugging. If you click the run button, that will run it. If you click the debug button, that will debug it. And then you can click the profiling button here, and that will profile that application based on the configuration which you've got selected here. So basically, you've got your choice of things. You can trace however you want to. You can trace based on unit tests, or you can trace based on command line parameters or whatever. And in fact, we've also got a very simple API for .trace as well. So you can bring in a .trace NuGet package, and you can have it so that you start your application under the profiler, but nothing is being captured. And at a specific point, you can call the API and say, start capturing now, do some work, and then say, stop capturing. And so you can actually profile just the very specific parts of your code that you want to do. So there's a lot of flexibility there in how you can profile and how you can trace information.
Okay, many thanks. Thank you.
No problem. Okay. I think that's probably us done then,
Yes.
is it?
Yeah, sure. Okay, then. Thanks, Matt. Thanks for your...
No problem. Thank you very much for having me.
All right. See you then.
Yeah.
Bye-bye.
Cheers. Bye-bye.
Thanks, Matt.
Thank you.
Thank you, Matt.
Thank you, Matt.
No problem.